Hello everyone. Today we are going to talk about Eulerian trail. It starts with following real problem. At that time, actually Euler lives in Königsberg, and there's an interesting question at that time. So first, let's look at the concise map of the Königsberg. There's a river flows in the city, and you have two banks, A and B. And in the river, there are two small islands, B and C. And to connect these pieces, they construct several bridges. So here the green part are the bridges. And at that time, there's a question that because the bridges are so beautiful, and for a foreigner, if they want to visit a city, they want to view all the bridges, but without any repetition. So can we plan a tour such that each bridge is visited once and only once, and that it ends where it began. And of course, you can enumerate other possibilities on the original map, but then you'll find that the question actually has a mathematical formulation as follows. So that's what grid science usually do. They abstract from the real problem the most intense part of the facts. For example, here, although you have the whole bank A, from point of view of Euler, it's just a point A. And island B, island C, bank D, also as points or vertices. And then the bridges between them can be abstract to the edges. Okay, now you have a graph like this, and then the question is, is there any closed trail that contains all the edges of G? So here G is a graph. Now it's a purely graph theory problem. Okay, before we do that, we would because this is a typical situation appear in reality. For example, if you have a postman want to deliver mails every day, so you have the similar problem. So a trail gamma is called Eulerian if gamma contains all the edges. Actually, this problem is quite easy. It's easier than the Hamilton cycle we are going to discuss later. So by easy, I mean you have clear invariant to control the problem. or a clear invariant give a necessary and sufficient condition for finding a closed trail. So before that, let's state the following technical lemma, which enlarges an edge to a closed trail. Let G be a general graph. Assume that the degree of each vertex is even, then each edge of G belongs to a closed trail and hence to a cycle. Here, let me explain a little bit on the degree even condition. So for example, if you have the following graph, and the degree at first vertex is 1 and then 2, 2, 1. And of course, the claim is wrong. So statement don't hold for this. Okay, so this is this shows that the condition is necessary if we want a statement still hold. And then why this even is important? This is because, for example, you have a vertex and you have a lot of edges. Okay, and when you draw a trail, you have some edge flows in, and then some edge flows out. Okay, if the degree is even, what does that mean? That means whenever you flows in, you can always find some edge flows out. You will not stop there. This is not the case for the previous graph, the line case, because when you flows in the endpoint, you never get out. Okay. So this is the reason why we want even. Okay, to prove it, we introduce the following algorithm. Actually, it's not necessary to use the algorithm. You can do it by induction, but probably it's easier to formulate this. So let W be a set of vertices. This is the place where we store the information of vertices in the trail. And F, set of edges. This is the place where we store the edge of a trail. And step 1, we put I equals 1. Step 2, put W equals x0, x1. So here, what is x0, x1? We should make a convention that here. So at the very beginning, we have an edge, alpha 1 equals x0, x1. record the problem, it start with an edge. Okay, and then step 3, and put f to be a set consisting of alpha 1. And step 4, so far we did nothing. And step 4, we run the program, and while xi is different from x0, we locate an edge alpha I plus 1 equals xi plus 1, not in F. And then B, put xi plus 1 in W. And here xi plus 1 may already be in W. And C, put alpha I plus 1 in F. D, increase I by 1. And then repeat step 4 again and again. And here we have 2 questions. Actually, if we want to use algorithm to prove the problem. So first one is, can we always run step 4? Secondly, if first question is true, then the next question is, will it terminate? And so look at question 1. So why this is true? So here the key step, actually the key step is 4a. So why can we always find an edge not in F, starting from one point xi in W? We noted that this is because the degree of each vertex is even. Okay, therefore, xi so when I equals so let's use some notation. x0, x1, x2, xi. Actually, in the middle, you might have already some xi appear, but at this point, we have odd number of edges incident with xi. Okay, and by this, we can always find a new edge incident with xi. New means that it's not in F. Okay, this is how we solve question 1. And then for question 2, this is easy because the kinetic of the edge set E is finite, while F is a subset of E, and each repetition, or let's say each time we increase the cardinality of F by 1. So this cannot repeat forever. And then next question is when it terminates. So from the program, it's easy to see. When you go back to x0, the starting point, the program terminates. Okay, and then from this program, after you solve question 1, question 2, and you terminate, determine what is situation when you terminate the program. You noted that you construct a closed trail because k is x0, and such that the first one is alpha 1, which is a prescribed edge. Okay, now let's work out this program by an example. So suppose you have the following graph. Actually, in the above theorem, we didn't show you why there's always a closed cycle. We will explain by the following example. So this is a general graph. And here you have B, A, B, C, D, E, G, F, H. Oh, sorry. I, X, I, A, I, W, F. So when I is 1, X1 is B, and alpha 1 is AB, and the W is set. Consider AB, and the F is AB. And step 2. So let's see. Step 2, from B, you need to choose an edge. So let's choose this one, BC. So here you have C. And then alpha 2 is BC points. W is ABC. And you have AB, BC. And from C, because has even degree, you need to note that the loop contributes 2 to the degree. And then from C, you find another edge outside the set F. So here you have D, for instance. Then alpha 3 is CD, A, B, C, D, A, B, B, C, C, D. Okay, then for D, you can find B again. So you have B, D, B, A, B, C, D. Because B is already in the set W, so even if you put in B, keep the same. And then for the edge, set F, you increase by 1. And then from B, you can choose a new one, H. So you have H. So B, H, A, B, C, D, H. And for F, you increase it by D, BH. And the next step from H, you can choose A, come back. So you have HA, A, B, C, D, H. Here you don't increase W. But for the set F, you keep all the edges from last step and add HA into F. Okay, and then you have a closed trail. A to B to C to D to B to H to A. And how to get a cycle? Because you see here B appears twice. Therefore, you can delete all the edges between these two repetition. So here you have a repetition. Therefore, you can just collapse. So which gives you A, because you collapse everything in between two B's. So you have this. If you have several repetitions, you can repeat this procedure again and again until you have a cycle. This is, you can always get a cycle. This is because the number of edges is finite, and every time you decrease the number of edges. Okay, this procedure cannot go on infinitely. It will terminate at finite step. So from here, you also see that in graph theory or in combinatorics or in computer science, the termination is very important. Okay, and based on this, we can state the following solution for the Eulerian trails. Suppose G is a connected general graph. G has a closed Eulerian trail if and only if the degree of each vertex is even. So here, since we have if and only if statement, we need to show two directions. The easier direction is as follows. Suppose G has a closed Eulerian trail. Then each vertex has even degree. This is because we can explain a little bit here again. This is because for any vertex whenever you have edge in, you should have an edge out. And whenever you have edge in, you have edge out. You have edge in, you have edge out. Okay, since it's a closed, so there will be no endpoint. Each point just the same if you rotate the position. So degree of each vertex is even. Okay, now suppose that each vertex OG has an even degree. And now let G1, we are going to construct just like by induction or by running some program. So at the very beginning, we let G1 be the graph. G, the original graph G, and then choose an edge. So no matter how, each edge must appear in your Eulerian trail. So you can choose an edge alpha 1, and then find some closed trail. And then the idea is every time you enlarge the trail a little bit, finally you get the whole graph. So choose an edge alpha 1 and apply the above lemma to find a closed trail gamma 1 containing alpha 1. Okay, now define G2 be V E2. V is still the vertex set, where E2 is defined by E1. Get rid of all the edge. Edge alpha belongs to gamma 1. Okay, and claim that G each vertex of G2 has an even degree. Okay, I leave this to you. And it's easy because since we have closed the trail, and the edges in the closed trail contribute even incidence to each vertices. And after you get rid of this, you just decrease the degree of each vertex by an even number. Okay, and so here I give a graphic explanation. So at the very beginning, for example, you might have a complicated graph and among the so let's draw a little bit. And this is alpha 1 you are choosing. And by run the program, around the lemma once, you find a closed trail inside graph 1, and then this is G1. And then G2, to construct G2, you need to delete those closed trails. So here, so you don't have the green part anymore. So this is G2. And then we are going to repeat. Again and again. And you hope that finally you will have an empty graph. An graph with empty edge set. Then you are done. Okay. And so notice that if E2 is an empty set, we are done. If E2 is not empty, then there is an edge alpha 2 in E2 such that alpha 2 is incident with a vertex Z1 on gamma 1. So why this is true? This is because the graph G is connected. Okay, then for this alpha 2, we can find a closed trail containing alpha 2 and define gamma 1 star gamma 2 and Z2. Actually, this is just joining gamma 1 and gamma 2. I should make a remark that here G2 might not be connected. We will not use the connectivity of G1, G2, G3. We only use the connectivity of G. So this is a subtle point, although not that important as some other issue, but it's still a subtle point. Okay, so define. So what is gamma 1 star gamma 2 Z2? This is gamma 1 plus gamma 2. In other words, if gamma 1 is so we can rearrange the gamma 1. Let's see. Okay. So if gamma 1 is x0, x1, blah blah, z1, blah blah, finally x0, and gamma 2 equals y0, y1, blah blah, z1. So let's see here, xi minus 1, xi plus 1, yj minus 1, yj plus 1, y0. Then gamma 1 star gamma 2 z1 can be defined also here. Oh, sorry, this is z2. Can be defined by x0, blah blah, x I minus 1 and yj j plus 1 blah blah y0, and then you go back to y1 blah blah yj minus 1. So here you should have xi minus 1 z2, and here you have yj minus 1 and then z2 and xi plus 1 blah blah x0. This is one way of defining this, and I should say this is not canonical. You can have some other ways to define it. For example, this is one way, and another way is you can first run or you can rotate it just like z2 xi plus 1 xi plus 2 blah blah x0 and x1 blah blah xi minus 1 and z2, and then you go to next piece yj plus 1 blah blah y0 y1 y2 yj minus 1 z2. This is another way. So you have just some rotating of the closed trails. Okay, and similarly, we define G3 to be a subgraph of G2, where the edge set E3 is E2, get rid of those edges. Edge alpha belongs to gamma 2. And then if E3 is non-empty, find alpha 3 in E3, which is incident with vertex Z3 on gamma 1 star gamma 2 Z3, and find gamma 3 closed trail containing alpha 3, and keep on, and then define gamma 1 star gamma 2 z2 star gamma 3 z3, and continuing until we get an empty subgraph. Okay, so you can fill in all the remaining details by yourself. And then next thing is, if you don't, so this gives you gives an answer to the Eulerian trails. The original question: can you find a tour with all the edges once and turn back to the original position? But there are also questions like, can you visit all the edges once without requiring the endpoint coincide with the starting point? Okay, then you have the following question. So, theorem. Suppose, let's say G has an open Eulerian trail if and only if there are exactly two vertices U and V order degree. Every open trail in G joins U and V. In other words, start with U and with V or vice versa. And the proof, you can repeat the above procedure once, but we have some detour to get rid of all the difficulty we already dealt with. So first, let's prove the easier direction. So if there's an open Eulerian trail, then it joins U and V of order degrees, and each other vertex has even degree. So here actually U is different from V. From graphically, it's easy to understand because suppose this is U, this is V, and you have one edge out, and whenever you have one edge in, again, you should have one edge out because U is not an endpoint, so you cannot stop here. Whenever you get in, you should get out. And similarly, when you get in, you should get out. And for the intermediate points, intermediate vertex, whenever you have one edge in, you have one edge out. One edge in, one edge out, blah, blah. And for the endpoint, it's similar to the starting point. Therefore, if you count a degree locally, it's easy to verify the theorem. Okay, next we prove the other direction. To do that, let G prime be a new, define a larger in large G. By this set, E prime, where E prime is E union an edge UV. Then immediately we can conclude that then G prime has the property that each vertex has an even degree. So this is a crucial part. You connect UV and you just change the degree a little bit so that G prime, the enlarged one, has even degree at each vertex. Then by the above theory, there is a Eulerian trail gamma of G prime. And so removing the edge UV from gamma prime, we get an open Eulerian trail gamma. So here I would like to use a circle version. Anyhow, so x0, x1, x2, this is gamma prime. And inside you will have u, v, x0 Okay, and then you are going to remove this part. But if you remove in this way, then you have how to say? If you remove in this way, then you just broke the gamma into two pieces formally. But then if you noted that this actually is a circle, that is, this is the same as also. You have the coincidence here. Then you after you remove UV, you have a open trail instead of two trails. So how to visualize this? So gamma, we rotate the position in gamma prime a little bit so that it starts with here UV. Let's see, VU. It's same thing, but I would like to make life easy. I will just do like this. Okay, then you start with U. Here you have X, J plus 1, XJ plus 1, XJ plus 2, blah blah, X0, and X1, X2, blah blah, V, blah blah, U. Okay, so if you rotate it in this way, then you just get rid of this one, which gives you an open Eulerian trail. Yeah, so actually the proof reminds you that the graph theory, not only the formal mathematical explanation or formal mathematical representation, you should also consider its graphic meaning. For example, here, for gamma prime, you might have, for a closed trail, you have a lot of representation by x0, x1, blah, blah, but the graph is unique. The trail is unique. Okay, and if you are brave enough, you can generalize it to the following theorem. Let G be a connected general graph. Okay, I can't remember if I... here I omit one important condition, that G is connected. Otherwise, you have counterexample. Yeah, otherwise you will have counterexample. So let G be, let G be a connected general graph. Suppose that the number of vertices of G with order degree is m, which is a positive integer. Then the edge of G can be partitioned into m over 2 open trails and no less. So the proof is quite easy. You just joining vertices order degrees pair by pair. You can always do that by the previous theorem, that the whole degree, so by the theorem that you have even numbers of vertices with order degrees. Okay, and so let's assume this U1, V1, U2, V2, UM, UKVK. Let's see. Yeah, UMVM. UM over 2, VM over 2. So M must be even. Okay, then let G prime be V E prime, where E prime is E union U1 B1 U2 V2 UM over 2 VM over 2. Okay, and exists a closed trio, Eulerian trio, gamma prime or G prime, and removing U1 V1 U2 V2 UM over 2 VM over 2 from gamma prime. So in other words, you need to break M over 2 times. So for example here, no matter how you cut one, two, blah blah, M over 2 times, then remaining you will have M over 2 connected pieces. So each of which are open trails are open trail. So we are done. Okay, a little bit more involved one is so-called Chinese postman problem. The name comes from the fact that a Chinese mathematician first raised this kind of problem. So let G be a connected general graph. Find a closed walk of shortest length, which uses each of each edge of G at least once. So this is a problem that in general you may have the situation that the degree of vertices of the graph E not even at all. You have a lot of order degrees. Okay, but for a postman, you don't want to just break the trails into M over 2 pieces. You are required to, no matter how, you are required to go through every edge at least once. So this is for a postman. If you have M over 2 postman, then you can always do that. But in reality, you only have a limited number of postmen. Okay, and under this condition, then a natural question will be how to find a trail, or how to find, it's not that, it might not be a trail, how to find a closed walk through each edge at least once. Okay, and then this problem has been solved by Edmonds and Johnson. And here we can have slightly not so efficient bound for the problem. So let G be a connected general graph. The kinetic of E is K, then there is a closed walk in G of length 2K. So in other words, at least you repeat every edge twice. At most, you repeat every edge twice. You can walk through all the edges. Okay, and the proof is quite easy. You construct a new graph G star such that E star doubles the multiplicity of each edge in E. So what does this mean? So this means if E is M1 alpha 1 M2 alpha 2 ML alpha L, then you define E star to be M2 M1 alpha 1 2 M2 alpha 2 2 ML alpha L. Then you see G star satisfies the condition that each vertex has a even degree, and then you can apply the theorem, which guarantees a closed Eulerian trio. Okay, I will now explain this more, because in reality, this also not so real. The problem is, even you have two different edges, their weight are different. Probably one is very long, just like the number 1 row along the west coast. The other one is quite short, just like the State Street. So of course they are different. So this is not so practical. A more practical way is to assign different weight to different edge. W on edges. And what we are going to do is minimize the summation of the weight. Of course, here the gamma visits each edge at least once. Okay, then it will be an optimization problem, and you need a lot of analysis tools to find a perfect solution. And of course, most of the time you need to put on some convex condition to guarantee a solution or equilibrium points. So this is slightly advanced than our course. And if you have interest, I highly suggest you to look for some reference for this one, or build up your reading report on these topics. Okay, I will stop here for this lecture.